And then the next thing that I'm going to explain is about variance. And variance has a relationship with the previous variable, which is the expected value. So variance helps us basically is a measure of spread. So this is really helpful to measure the spread in our data. So that's what variance does. And for example, let's say you have two house here, okay? And this is, let's say here you have first, let's say this is first house, and then the second house. In coordinate, it's located in -1, and this one located in +1. And then if you look at for the uh, expected value, then it's for sure it's going to be 0, right? How about this second case, where we also have two houses which located uh, in a different coordinate, but in this particular case, these two houses are located far away. So if we try to measure them with variance, then it turns out they also have expected value equals 0. So we basically want to say that these two houses, okay, between A and B are different, meaning we cannot say they are the same because they have the same expected value. So we have to find a metric that can help us to describe that the spread of these two variables between variable A and variable E, I mean case A and case B, is different. It's totally different. And the way to do this is by using the variance. So variance, okay, can help us to measure the spread, and it can be usually we can denote this, and the formula is e x here, e x squared. This is the main formula of variance, okay? And this also means ex squared minus x here squared. So this is the formula of variance. And then another thing that it's also important to measure to describe our data is standard deviation. Yeah, standard deviation. So if it turns out variance itself is not enough to measure the distribution, because if we measure the height of the people, then there is a unit like meter, then in which we must square root this unit letter to measure spread variance. So in order uh, to to measure the distribution when it has units, then we're gonna use this standard deviation. So basically, standard deviation gives us the square root of the variance, because we really want to eliminate the roots, not the roots, but the power of 2 the quadrant, because if we quadrant the variance, then the problem when it has units, then uh, it will give us the issue of the statistic. So that's the third variable that we have to understand here before we jump deeper into the machine learning. And then the the fourth thing is about the standardizing a distribution. Standardizing a distribution, which also essential because uh, in machine learning, you always try to standardize our uh, data because it's either a common practice and also it turns out standardizing our data really helps our machine learning learns faster. In other words, it can accelerate the performance, which is really beneficial, especially if you're dealing with a high amount of data. So for example, here you have a data set. Let's say this is your data here, and then you have mean of this data equals to this one, mean, and then this is the mean position when it's equals to 0. So this is the distribution of data, and then in order to bring this, okay, to this position, then what we're supposed to do is we need to, I'm sorry, we need to we need to uh, subtract our x, big capital X here with mean. And why subtracting this expects that we will get means equals 0. Why? So I can write the proof here. So remember the expectation is linear. So we have this uh, properties here. And herein we have x minus mean. Okay, since y itself here is mean, and then sorry, ex will be e mean here. So we know this will be equals to mean since this is a constant. Okay, and then we have x here equals mean, and also e of x is also mean, so we have equals 0 here. That's proof that our data is correct when we have this equals 0. However, we also want our data to have standard deviation is equals to 1. Okay. Um, so after we move the uh, after we move this and it's already x, and we want the standard deviation equals to uh, 1. So this is our standard deviation now. So how do we obtain standard deviation equals 0? So we have to divide the x with this standard deviation to make it 1. So we want it to become 1, and after we centering, then basically what we're gonna do, we will. I'm sorry. This is what we're gonna do after we obtain standard deviation equal 1. So we scaling the distribution of our data. So it's like shrinks our curve here to make it like smaller. So it just make it standard deviation equals 1. So this is what happens when the STD or standard deviation already 1. And then one might okay. So if we look at our So this, I want to give you a little proof that variation here, x divided by standard deviation, how come this becomes 1? So we'll call the variation x here. So sorry. And then it will become this one variation of x here, and then it will be 1 per x, then sigma divided by sigma will be equals to 1. So this is exactly what we have. Okay, so uh, that's how we standardizing our data sets, and it's also important in machine learning, and we're going to find many uh, applications in machine learning where we really want to standardize our data. It's a common practice, but it turns out that this practice really helps us uh, to optimize our machine learning model. And then the fifth things is the skewness and kurtosis. Okay, so we already capable to describe our distribution of data in various ways using expected values, using variance, using standard deviation. Now, there's a problems, but there are some subtleties that we haven't um, described. And this is where the skewness and kurtosis takes place. So I'm going to jump into the equation used for skewness here is basically stems from the expected value of x cubed. So skewness, this is the main value, okay, divided by standard deviation square, cube. And then what gives us is, there's this brings enough information. So if this larger than 0, that means it will be positively skewed. So our data will positively skew, meaning this is our data. And then if x here is smaller than 0, then this is gonna be negatively skewed. So this is negatively skewed. And if the data is 0 here, if equals 0, then basically our data doesn't have skewed. So it's perfectly like bell curve shape. Okay. So this is the interpretation of skewness. And then the last variable that I usually, not me, but most people use to describe their quantities is the kurtosis. Okay, so for kurtosis, it has this it's derived from the uh, expected value to the power of 4. So here we have x divided by sigma 4 here, and it tells us another information, and we can use this kurtosis to so basically this is the easiest way to explain it. So if your data looks like this, distribution of data looks like this, for example, here, then it basically has the small kurtosis. But on the other hand, if your data has this pigtails, okay, so meaning pigtails, then basically this has large kurtosis. So that's all parameters that we can use to describe our distribution of the data.